Hi, welcome to Physics 2211 Lab 5 on the Falling Slinky. My name is Maria Jyotish, and let's get started. The purpose of this lab was to observe the motion of our slinky stretch due to it falling from rest, and then to construct a computational model based on physics principles which we can compare our observed data to, and determine whether the bottom of the slinky stays stationary in the model. Some fundamental physics principles and models we can see in this lab are Newton's second law, the momentum principle, which relates to net interaction between the system and its surrounding to the observed motion. We also see in our observational model that the net force, sum of all forces, may be impacted by the presence of the drag force, whereas in our computational model we see the net force is equal to 0, as no other force besides tension and gravity impacts the object. And for a brief preview, the two models, observed and computational, will show the slight impact of external forces causing discrepancy between their data. However, the bottom of the slinky does stay stationary. Some physics ideas we will see in this lab is Newton's second law, as mentioned earlier. Using this, we will calculate that the net force is equal to the force of gravity plus the drag force and the force caused by the slinky. The drag force, which is resistance caused by the motion of a body through a fluid like air, gravitational force pointing down and equal to mass times the gravitational constant, the slinky force, which is tension pointing up, and the position and velocity update formulas are used in our computational model to update movement. Here I use Tracker to analyze the motion of our slinky. To track the slinky, I measured the position of the center of mass, which was set to be the bottom of the slinky, in each frame. In the video you see that the bottom of the slinky stays in the same position until the top of the slinky gets near it, at which the whole slinky begins to move towards the ground. That's why if you look at the y position versus time graph, it initially stays constant and then slopes downward. Next, I use GlowScript to create a computational model of the slinky's motion. First, you can see I set the slinky's initial position and velocity based on our observed data. Then I added the gravitational constant and proportionally constant for our drag force. Then down in the first while loop, I set the code to run for the time period it took for the top of the slinky to reach the bottom. In the loop, you can see the gravitational force and the slinky tension force were equal, which is the reason behind why the slinky remained motionless until the top reached the bottom. Next, I used the position and velocity update formulas to update the slinky's position. In the second while loop, the time is set from when the top of the slinky met the bottom to right before it reached the ground. The main difference in this loop is that the weight force and drag force are not equal, which is why the slinky started moving downwards. Next, taking the observational and computational data, I used Excel to create a position versus time graph to compare the results. You can see here that initially both datasets aligned, but then later began to diverge. This is most probably due to the external forces acting on the object in our observational data that weren't taken into account in our computational model. But ultimately, we can see from the graph that the bottom of the slinky in our computational model moves nearly at the same time as our observational model. A source of error could have been incorrectly plotting our tracker data. Some follow-up questions are, why is the bottom of the slinky initially stationary? This is due to the forces in the y direction canceling out. The tension force of the slinky is similar to a spring and counteracts the gravitational force, which is with equal and opposite magnitude. Next, what if we added a weight to the slinky? Depending upon if the tension force of the slinky is higher, the slinky may or may not stay stationary. Thank you for watching.